So I'm going to begin with a review, and then I'll talk about the new work and try to emphasize some of the things that will help you with other presentations here at this meeting. Stefan obtained a PP seismic image from Geophysics, and it came with, I was going to say APS image, but really this is what we call the PS1 image. And these are Stefan's slides. He just called it the PS image here because it's all he worked with for most of his research. And he's displaying the PP image and the PS image with different time scales so that reflectors are more or less aligned. Okay? So this is not what we mean by warping. This is just, a constant squeezing or something that might be appropriate if VP-VS ratio was constant everywhere. And of course we know that's not true. And so he estimated using this process that we call smooth dynamic warping. Okay, so that's dynamic warping, but with the time shifts constrained to be smooth in both the vertical and horizontal directions. He estimated these time shifts from those two images, right, and then was able to warp the PS image to PP time. And so now we have both the PS image and the PP image on the same time scale, and I'll just flip back and forth and you can see the differences. Now, you've seen many of these types of displays before, but just as a reminder, the picture in the upper left is a horizontal constant PP time slice, and after the warping, it's actually much more similar to the PP image than it was before the warping. Inline cross-line sections are shown below, and the one point where all three slices intersect is the intersection of the yellow lines you see displayed here. Okay, so these were two 3D images, and they were aligned by these time shifts, but these time shifts carry information about the ratio of P wave velocity to S wave velocity. So VP-VS can be computed by taking derivatives of the time shifts that you see displayed here. And this is why it's important that those time shifts be smooth, because otherwise these derivatives would be really erratic. And Stefan displayed that very nicely last year. Now, he did some other things here which are in his thesis, and I encourage you to read it to get these displays. But this, if you were here at the meeting last year, you saw this picture. Okay, so the goal in this dynamic warping is to take this other image, in our case it's the PS image, and warp it to match the PP image. And to better explain that process and the new part, let's just focus on two seismograms and not images. It'll just be easier to understand what's going on if we just think about two traces. Now these are synthetic traces, and there's been noise added so that the differences between these two traces are not due to time shifts alone. Right? And that's important because we know that in practice there are going to be differences. In fact, we care about those differences between PS and PP reflection coefficients, both in magnitude and phase. All right, so the first thing we do is, before I say that, notice that the time scales, again, are different. One is PP time and the other is PS time. All right, so the idea is that for any choice of PP time, and here we're choosing a relatively strong reflector at about 0.7 seconds, there's a corresponding reflection in the PS image, and you'll see that's at a larger time. Okay, that'll be the PS time. And the relationship between the two images then is given by what we call the shifts, the U, and from those shifts, which are a function of PP time, right, we can easily get the PS time. So that's the model. And dynamic warping is a way of producing a sequence of shifts as a function of PP time. So that's the U function. When we sample it, it's going to be a sequence of numbers, a sequence of shifts that will optimally align the PS image and the PP image. Okay, so when I say optimally, of course I have to be thinking about some metric for good alignment. And that leads to this really important first step in every application of dynamic warping, and that's the computation of alignment errors. Okay, so here is a display, and you'll see other displays like this. I'm going to spend a little bit of time explaining how we compute this image above. Below, you just see the PP seismogram for reference, a function of PP time. And so the idea is if you don't know what the time shifts are, you try them all. Right? For every PP time, you just try every possible time shift. And in this case, you're actually including some time shifts that could not even be possible. Now, you notice that I did not include any negative time shifts, because that geophysically it doesn't make any sense. And one of the beautiful things about the dynamic warping algorithm is that it is easy to impose, it's very natural to impose constraints on how we compute that sequence of shifts, and most importantly, to connect those constraints back to geophysical parameters, constraints on something like VP-VS ratio. So we know that there should not be any negative time shifts because PS times are always greater than PP times. We also know something else, and that is that the time shift function must always increase with time. So the slope, right, is also constrained, and that constraint is again very easy to impose. These are hard constraints. It's not like regularization. We're saying, well, we want a smooth shift function. We do want that for other reasons, but we have hard bounds on constraints that are connected to geophysical parameters, like in this case VP-VS. And you'll see other examples at this meeting where those constraints turn out to be really important. All right, so how to interpret this plot? Okay, so let's go back to the two seismograms, PP and PS, and pick a PP time of 1 second, right? And so the first thing we'll do then is for that time, we'll compare it with the PS sample at the same time. So this is like no shift. So the shift is here, it says 0.0. And we could do that again for a shift of 0.5. Right? So these are alignment errors. You'll notice it's just the difference between samples of the PP and the PS traces shifted. Right? And here's the third one. Right? So now that's just 3 of many possible combinations. And if we look at these 3 examples in that plot of alignment errors, they correspond to the locations of the white dots you just saw. Right? So that's a PP time of 1 second with shifts of 0, 0.5, and 1 second. Do that for all PP times and for all the shifts that you see here, and you've got this array of alignment errors. It's really easy to compute. It's a little hard to understand if you haven't looked at it before. Notice that a lot of features in this array of alignment errors are vertical. Those correspond to features that have a constant PP time. And if you look, you can probably see that the higher amplitudes, the redder hues, correspond to peaks in the PP trace that you see below. Likewise, the diagonal lines correspond to large amplitudes in the PS seismogram. Right? And so those are just lines of constant PS time. And you will see different patterns of these intersecting lines in these plots of alignment errors depending upon what the vertical axis is. It doesn't have to be time shift, right? It could actually just be PS time, right? But that would actually create a much bigger array of alignment errors and therefore waste computation time. And so that's why we parameterized it this way. But again, you'll see other parameterizations, but the basic idea is the same. You just sample by sample, subtract samples from the PP image, the PS image, or one sequence and another sequence, and build up this array. All right, so that's the array of alignment errors. Now, the part that I'm really not going to try to explain is the dynamic programming part. The name dynamic warping, you might think of it as, means that we're not talking about static shifts, we're talking about dynamic shifts. Don't think that way. I mean, it's actually true, because if it was a constant time shift, it would be a much simpler problem. But the phrase, the word dynamic in dynamic warping really comes from a classic algorithm in computer science called dynamic programming. And some of you I know this algorithm, and you may have even used it in different contexts. I rank it up there like with the FFT. I mean, it's that useful. And yet I don't think there are that many applications that people have looked at. So it's perhaps worth looking more closely and thinking about that algorithm, because it solves a global optimization problem. And that problem is to minimize the sum of alignment errors that you see here along some path. And that path is going to be the shift function of PP time. So you just imagine it, and of course, in this case, where are you going to start walking, right? I mean, the PP time is 0, the PS time must be 0. So you're probably going to start walking in the bottom corner. But that's if you actually got the datums just right, and it's not real clear that you know for sure any point on this curve. But your goal is to find a smooth path through this array of numbers so that the sum of the errors along that path is minimized, right? And there's going to be a lot of local minima that you could get into. And the beauty of the dynamic programming algorithm is that you will find the global minimum, right, every time. And you have those hard constraints that I mentioned before. Okay, so think of the reddish hues as like big hills that you want to avoid, and you've got to find the optimal path through this array. Can you see it? Can you? I mean, some of you may have actually seen, and you might know where to look. It's synthetic, and so that helps. Okay, well, here it is. Right? So these are the known shifts. Maybe if I go back, right? Can you see it now? It's amazing how once you know the answer. Yeah. Okay. And that's just the scale at which I'm plotting here. But this curve here does correspond to the known shifts and the estimated curve. And those shifts were designed to correspond to a realistic situation where VPVS ratio might start off rather high and then decrease with time or depth. All right, so here are the estimated shifts and VPVS ratios. Okay, so how do we get the VPVS ratios? We need to compute derivatives of the smooth path, that's the U function of PP time, with respect to PP time. Right? And there's a factor of 2, and you have to add 1, but that's not important. What's important is that because our smooth path is here piecewise linear, the estimated VPVS ratios are piecewise constant because we computed a derivative at every PP time. Okay, so this was just one of many examples that Stefan showed in this context of what we call smooth dynamic warping, being able to force a smoothness constraint. And I think that's pretty much the end of the story. That's the review part. I want to get you now to the new part, and to do that, I'm going to summarize the key steps here, right? So the notion is we have two sequences, a PS trace and a PP trace, and we're finding a sequence of shifts. There's that U function at PP time again that will optimally align those. And so dynamic warping produces the quantity underneath that red arrow there. All right, and the way it does it is by minimizing the sum over PP time of alignment errors along some path. So we're minimizing with respect to a sequence of numbers, this sequence of shifts U, to minimize the sum of alignment errors. All right, so how does this change now when we have 3 sequences? All right, because we do. In fact, for the data that were provided through geokinetics, we actually did have a PS1 and a PS2 image, right? And so there's some interesting processing that we don't know all the details about how do you create those images and what do they mean and so on. But you can imagine that the PS events should arrive later than the PP reflections, and PS2 reflections, because the S2 wave is slower than the S1 wave by convention, they should arrive even later. Okay, so how could we find those shifts? Because the difference in shifts between PS1 and PS2 can be meaningful, and others have written about how to interpret those differences. Okay, so one way to do it would be to just take the PS1 trace and warp it to the PP trace, and you've already seen the result of that. But I'm now calling this U1 because I'm being accurate, because the PS image in this case was the fast shear wave image, the PS1 image, right? All right, so that's one sequence of shifts. We could get a different sequence of shifts if we did this, right? We could do this. We could just use the PS2 image instead of the PS1 image, right? So now, what are the sequences so far? Are U1 and U2. Of course, there's a third because we've got three sequences. We could warp, same stuff, right? Use the same process to get another function. I'll call it US because it's really shifts from PS2 to PS1. So what's common is the S, right? So US, and I put a tilde there because I want you to recognize that if you do this, the shifts you get will not be a function of PP time. They'll be a function of PS1 time, right? And that's actually probably not what we want. But here's the summary, right? So we've got three traces. You can think of it as three images, but let's just keep it simple and think of three seismograms and three shift functions, right? So just do that, right? But here's the catch. In theory, you actually expect that U2 is a function of U1 and US, right? And notice that now I don't have the tilde on US because US in this expression is a function of PP time. And you can get it if you have U tilde, right? So it's not a big deal. You have to interpolate the shifts is what happens there. All right? So this is in theory what should happen. And if you actually use noise-free synthetics, you can make this happen. But if it actually ever occurred that the shifts you got from the PS2 and the PP image actually satisfied this equation, I'm paraphrasing Ken Larner a little bit, but it wouldn't be geophysics, right, if it actually worked that way. In practice, they're not going to be equal, right? So what are you going to do now, right? How do we reconcile the differences? Well, it turns out that dynamic warping has a way of dealing with this. And I'm going to show you what that is, right? So let's change here's the constraint we want to impose. We want, because theory suggests that it should be true, this U2 to be given by U1 and US. Right? And by the way, U2 doesn't have to be the one that you solve for here. You could say US is a function of U2 and U1, right? It's real easy. But let's just write it this way for definiteness. And then simplify notation by getting rid of the subscript PP. So now when you see time, it's PP time. Because that is the reference time. We always are correcting towards PP time. All right. Here's what we could do, right? To ensure that the sequences U1 and US, right, would give us that consistent U2. So notice that in the definition of alignment errors now, something's changed. Alignment errors are no longer just a function of U or U1. It's the same thing. They're also a function of a second sequence, and those are the US's as a function of time. The alignment errors are only indirectly a function of U2 by the equation you see up above. All right, so we're going to use a lot of the machinery you've already seen for three sequences. The alignment errors are defined below with some weights that you could choose, W1, W2, and W3 there. I think in examples that I'm showing you, Stefan just set those to 1. But you can well imagine that you might give lower weight to the two PS images because they're noisier, or maybe you would give them more weight, right? Depending on how deep your target is. All right, so it's just possible to put weights in there. All right, so there's no U2 anywhere below here. Right? It's just going to be a byproduct. You can just add the U1 and US shifts. Now, the array of alignment errors, think about what's going to change now. It's not going to be a function of, it's going to be a function of PP time. It'll be a function of U1, but also US, right? And that's going to give us a three-dimensional array of alignment errors. Okay, so the long axis is the PP time, the vertical axis is U1, and I guess the short horizontal axis is US. Right? So this is just a three-dimensional display, and now the optimal path of shifts, right, as a function of PP time, right, the optimal path is going to have a U1 and a US for every PP time. And here are the estimated shifts for the synthetic traces that I just showed you. Okay? Again, found using dynamic programming to work our way through this array of alignment errors to minimize the sum of errors along this path, which is constrained to be smooth and also constrained to be geophysically, reasonable. Right? All right. Let me show you the results more closely here. Right? So this is the result of warping simultaneously the PS1 and PS images to the PP image. I say images, they were just those traces you saw before. At the top, you see the noise-free result. The correct answer, by the way, in every slide from now on is going to be the dashed white line. And so U1 here is displayed in red, and you can see for the noise-free case, it works just fine. And even when the signal-noise ratio is 1:1, one of the benefits of dynamic warping is its robustness in the presence of differences that are not related to time shifts, like differences in the wavelength. Right? We are not using what Chris Graziano talked about this morning. We need the shifts in order to get the wavelets, right? And we seem to be able to get pretty good estimates of shifts, even though we're squeezing here. All right, so this makes sense. I mean, these results are pretty accurate. Here's what would have happened if we just used the PS1 image and the PP image. Right? And you'll see there's something went wrong when we had noisy traces at between 0 and 0.5 seconds there. Okay, now let's look at U2. Right? Again, you can solve for U2 after you know U1 and US, and the solutions here, both for the noise-free and the noisy case, are really close to the known shifts, the dashed lines. However, if we were to just compute U2 by looking at the PS2 trace and the PP trace, aligning those, the noise would cause significant error that we're able to eliminate by solving for, in effect, all three shift sequences simultaneously. Okay, so this is just looking at two of the seismograms. So we're not using all the information that's available. The other information that's available is the PS1 image. Right? And that carries information about U2, somewhat surprisingly. Okay, and finally, here's the US example. And it doesn't seem too bad, right? When you just align PS2 to PS1, it's pretty close. Right? But those were the main results that I wanted to share with you, and that Stefan would have liked to share with you today if he could have been here. And just to summarize, the idea is to extend dynamic warping to aligning 3 sequences instead of 2. And what I've just at the very end shown you is that the results can be more accurate if you do this, because you're actually using all the information simultaneously as opposed to solving 3 independent optimization problems. However, and Stefan really taught me this because he was the one who was trying to make this work and work for the 3D images that he had. It's significantly more costly. If you notice what happened, the array of alignment errors grew an extra dimension because we added a 3rd sequence. If we added a 4th sequence, it would now be a 4-dimensional array. What this means is that the computational cost, both memory and compute time, grows exponentially with the number of sequences you try to align with this. Now the good news is for PP and PS1 and PS2, maybe that's it. We don't have more. But you're going to see in a moment an example of trying to use dynamic warping for a similar problem where we've got lots of sequences, right, that we're trying to align simultaneously. And this work here really taught me that we need another solution. This is not going to work when you get above 3 or 4 sequences. I say it's not going to work. I have heard of someone actually doing this for 10 sequences. Okay? That means they had like an 11-dimensional array of alignment errors, and they did it, and I think they just did it so they could say they did it, which is maybe good enough. Right? Thank you. I'm going to stop there and take any questions you may have.